when they're in high school or middle school. So to that end, algebra really matters. But let's say you're more of a skeptic and you say, look, it's all about STEM, right? STEM, 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 STEMmy, STEM, STEM. If I want to have a kickball field, I'll write a STEM grant and just slap the word STEM on it, and that's how we get the money for it. STEM is really important. We all love STEM. Well, something people don't often realize is that Algebra 1 is really the gateway class to all STEM fields. And so if a student fails Algebra 1 and decides, you know what, I'm not a math person, I stink at math, yeah, obviously they're not going to go on to calculus. So we understand the connection to the M part. But what people often forget is that if you don't do Algebra 1, a student's also not going to be modeling projectile motion in physics. They're not going to be balancing chemical equations. They're not going to be looking at population growth and rates of change in biology. And they're certainly not going to be computer programmers. So to the extent that any of us have a stake in STEM education, all of us really depend on student performance in algebra. A 2004 study looked at the correlation between Algebra 1 performance and future earnings. And it turns out that for the cynics out there who are telling me, Emmanuel, you know, to heck with this math nonsense, it's all about the Benjamins. Well, I've got news for you. This study found that the grade you get in Algebra 1 is the most significantly correlated subject of any for the amount of income you get for the rest of your life. So Algebra 1 is pretty important. And then finally, for the hardcore cynics out there, we live in an era of high-stakes testing and standardized tests. And whether you love that or you hate that, unfortunately, we all have to just deal with it. And high-stakes tests in most states often have like an English language arts component, and they often have a math component. Those are usually the two. And of those two, which one is it that politicians and superintendents and parents read about in the news? It's the math. And it's not just any part of the math. It's not just like the, you know, the arithmetic or the fractions. Typically, it's the algebra, right? It's the word problems, the functions. So, you know, if you bought any one of these four reasons, you're sitting there understanding that algebra really matters. And if algebra matters so much to us, how do we feel about it as a society? We're sort of terrified, right? And it's this funny thing that, like, all of us understand that algebra stinks. All of us understand that it's this traumatic event for us. And you know, just by putting up this particular slide, a train leaves Chicago at 6 p.m., traveling east at 50 miles an hour. I don't even need to finish that statement, and everybody sort of understands what I'm getting at. So that just seems wrong. If it's so important, why do we as a society hate it so much? Well, to understand that, you got to understand why algebra is so hard and what math is to a young child. I know that, you know, a lot of the folks that might be on this conference right now are perhaps game designers or programmers or software engineers or teachers who are trying to create the next generation of those careers. And I think everybody sort of understands that real engineers don't invent solutions and then go around looking for problems, right? The first thing you do is you figure out what is the problem we're trying to solve, and then you build a solution for it. So what this slide is all about is, well, what if the problem is, why is algebra so hard, right? Let's understand the problem. So put yourself in the shoes of a 3-year-old or a 4-year-old. So at that age, math looks a lot like this. Someone says, hey, what's 4 plus 2, right? Can you solve the thing in red? 4 plus 2 equals blank. And so we'll do a little audience participation here, since I know that some of the folks on this conference have the ability to respond in real time. So those of you who can talk, anybody want to solve the thing in red here?
Sure, we'll go 6.
Fantastic! Oh, well done, little boy. Well done. And again, so you're a 4-year-old boy here, and tell me, young man, how did you solve this? What did you do to get the answer?
I counted on my fingers.
Beautiful, beautiful. Yeah. So what we learned at this age was that you can hold up, 4 fingers and then 2 fingers, and then you count all of your fingers and you get 6. And what we learned there was that math is a process, right? That's what math is. You carry out some process and you get the answer. And if you're good at math, that means you're good at the process. And if you're bad at math, that means maybe you're not so good at the process. But everyone, whether you got the answer or not, learned the same lesson. Math is a process. And as we got older, this process got more complicated. Suddenly it involved subtraction, multiplication, division, order of operations, exponentiation. But every step of the way, every time we saw a piece of math, it was the same. Turn the crank, execute the process, and get the answer. So then we get a little older, and math changes slightly, and now it looks like this. So once again, boys and girls out there, maybe now you're 8 years old. Call it out. Who can solve the thing in red?
We're thinking. The answer is 4.
Fantastic. Well done. Well done. And can you tell me, young lady, how did you figure out that it was 4? What did you do?
I think I probably used my fingers as well.
Okay, so maybe you held up 6 fingers and then took away 2 or something. Or you asked, how many fingers do I need to add to get to 6? But once again, you were executing a process and you got the answer. And everyone on this video conference who was able to get the answer can feel great. And everyone who struggled maybe feels a little bad. But again, what's amazing is that both groups, the ones who feel good and feel bad, they both agree that math is a process. So then we get a little older and we take pre-algebra. Uh-oh, pre-algebra. This is about to get weird, right? No, not actually all that weird. In fact, it's kind of the same. All we're doing is substituting, we're putting a letter as the unknown instead of a blank. But it's the same thing, right? You're still getting x equals 4. Math is still a process. So then students get a little older, and now they're about to take Algebra 1. And depending on what state you're in, this could be an 8th grade subject, this could be a 9th grade subject. And so students have seen hundreds of thousands of pieces of math at this point. And remember, all the students agree, whether they love math or hate math, they all agree that math is a process. I show you something in red, your job is to get the answer. And all of a sudden they take Algebra 1 and they see this. So what's the answer, kids? Is it 5? Is it 17? What's the answer here? And those of you that are math teachers or are familiar with, if you can remember your Algebra 1, you're probably scratching your head saying, what is Emmanuel talking about? What do you mean, what's the answer? And you're right. You're right to be scratching your head. I mean, there's still obviously a process here. We're adding 2 to something. But the reason that there's no answer here is because this isn't a question anymore. This thing in red is no longer just a process. Instead, it's describing an object known as a function. And in this case, the function is named f. It takes in a variable x, and then it adds 2 to it. So for students that are sitting there saying, math is a process, I got to get the answer, when they get to Algebra 1 and see this sort of thing, they're sitting there going, oh my God, I don't even know what the question is. How am I supposed to get the answer? And the sad fact is that there is no question. It's not that math has gotten harder, it's that math has changed. And believe me, it only gets weirder after this, right? In Algebra 1, teachers don't just ask kids to compute numbers. Suddenly they're saying, well, let's talk about this function f. Is it linear? Is it exponential? How many roots does it have? Is it 1-to-1 or is it onto? Does it pass the vertical line test? And these are all questions that if you're a student who's sitting there trying to get the answer, thinking math is a process, again, they're not just hard questions, they don't make sense. And so I think that one of the biggest challenges for students of algebra is understanding that we're no longer just talking about math as a process, we're talking about it as objects. And it's not just me who thinks this. So any of you who are out there who have Google Scholar pulled up on your another tab, you should definitely check out the work of Anna Sfard or Leonore Linchevsky or Jerry Confrey. Researchers in the 90s did a lot of work at this process-object jump that's introduced in algebra. And that's the first big reason that students start to struggle with algebra. But it gets worse, because these functions are so abstract, these objects, that we can't even look at them directly. Instead, we show kids, well, here's a function as a bunch of symbols, or here's a function as a line on a graph, or here's a function as a table, right, an input-output table of discrete inputs and outputs. Or we ask kids what the image of this function is. Is it 1-to-1 or is it onto? And we show kids this idea of a function as a mapping between domain and range. All 4 of these representations are different ways of looking at a function. But guess what? None of them are the real function. They're just different ways of viewing it. And that's cognitive challenge part 2 for kids, right? Not only are these functions abstract, but they have these multiple representations, each of which is a way of looking at the same function. So that's getting, the cognitive load here is pretty high. And I'll just give you a really quick demo. I mean, so this is a question that our students are seeing in math class. We might show them a function f and say, how many roots does it have? And I can show you f as a table. I can show you f as a symbolic formula. I can show you f as a line on a graph. And all three representations are equally good ways of looking at f. But which one of these representations is going to actually help you figure out how many roots it has? Well, the easiest one is the graph. I can just sort of look at the graph and I can see clear as day that that line crosses the x-axis in 2 places. So it's got 2 roots. But a lot of kids, they don't think of the graph as the function. They think of a graph as the thing the function draws. Especially the honor students. Oftentimes those kids will say, no, 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 give me the real function. So what they want to look at is this middle representation, the symbols. And those students, yeah, maybe they know the quadratic formula and they can figure it out. But even for them, if they're rushed or they're stressed out or it's a high-stakes test, there's more room for error. And what about the students who aren't the honor students, the ones who don't jump to the quadratic formula? So when I was a math teacher, a lot of those students, whenever I would show them a function like that, they would say, hold on a sec, Mr. Schanzer. They'd pull out a piece of paper and they would draw a table just like this. And they'd start plugging in numbers to see, if I plug in -5, what do I get? If I plug in -3, what do I get? So they're thinking about it as a table. But if their job is to find out how many roots f has, turns out this table isn't going to get them the answer at all. Right? It's not just that these representations are like equally good and you can pick one willy-nilly. It turns out that part of getting good at algebra means understanding that there are multiple representations and being able to choose the right one at the right time. So that's what the research says, right? If algebra matters to you for one of those 4 reasons, and if you know kids are struggling with algebra and you want to help, what do we want to do to fix it? Well, we got to make representations of functions concrete. We got to make them connected. And it's not just me who's saying this, right? Like if you look at NCTM, this is stuff that they've been saying for years. Common Core standards are all over this. If you're down in Texas, the TEAC standards are all over this stuff. This is just sort of what math researchers and math teachers know makes for good math instruction. So what does this have to do with programming? Right? How can games help this? How can we teach kids to make games and fix this? So I thought, well, gee, programming has functions, right? Programming has functions. Algebra has functions. If we just teach kids how to program, boom, we'll be all set. Suddenly they'll understand math. And it turns out I'm not the first person to think that, not by a long shot. So some of you might remember Logo. I believe it's 1969. Seymour Papert, Larry Forzig, and some other authors published the first paper on Logo, where they announced that they had this new language that's designed for kids, and they laid out 4 learning outcomes that kids would get by using Logo and learning to program. And one of those outcomes was algebra. And decades later, we've tried all kinds of languages to get kids to learn some sort of algebra or math. So we've got C++, Java, Python. You've got Alice in the middle here. There's a great language called Boxer down in the right-hand corner that's really cool. And sometimes we taught these languages explicitly to teach math, right? We literally told kids, oh, if you learn this language, it'll probably help you with math. Or maybe we did it implicitly, right? So we had a math teacher teach the programming class, or we shoved the programming class inside the math department, or we made it count as a math credit. One way or another, we communicate to kids over and over again that programming is going to help you with math. Well, it's been about 40 years since we started doing this, and we've taught a bunch of programming, so presentation over, right? Problem solved. Everyone in America is doing great with algebra. Not quite. And this was pretty interesting. There's some famous research that was done, in particular, again, for those of you who are on Google Scholar, check out Roy P's work with the Bank Street study, which looked at algebra transfer outcomes from the Logo group. And it turns out that if your goal is to teach algebra, you better make sure your language is actually algebraic. And this is something I run into all the time. People say, can programming teach math? And my response is, what do you mean? What is programming? Because programming is so broad. There are so many different languages that can do all different things. So if you want to make sure you keep using the best language for their job, what if your job was helping kids with math? And it turns out a lot of languages that we use nowadays are actually terrible for helping kids with math. And I'll give you an example. So for those of you out there in Cyberland, here's a simple program. It's 2 lines of code. So take a look at that for a second. And my question for you is, when I execute this program, what is the value of x at the end? So think about that just for a second. I click run, And at the end, anyone want to tell me what's the value of x? Tatiana, you want to give it a shot? Can anybody hear me?
Yeah, we can hear you. She typed in 3.
3, aha! Yes, you're absolutely right. So 3 would be the right answer here. Congratulations, it is indeed 3. For those of you that are math teachers, this is really problematic, right? This isn't just a little wrong. This is severely wrong, right? If a student says 3, you'd say, gosh, instant IEP. Because what if you look at the second line? What if you subtract x from both sides? You get 0 equals 1. That doesn't make any sense. And in fact, how can x change, right? You can't say x becomes x plus 1. That's not math. So this program that's sort of like brain dead obvious if you're teaching programming is completely screwed up. It's like brain dead wrong if you're teaching math. And the problem here is that x is not a variable. Right, so those of you that teach programming or that are into programming, I know that we love calling x a variable, but I'm sorry, it's not. It's a parameter. Variables can't have their value changed. And it gets even worse when you get to functions. I mean, don't even get me started. Programmers used to call them procedures, and then for some reason we started calling them functions, when they are not. And I'm not just making some sort of silly hair-splitting argument here. Functions and variables mean something really specific in the math realm. And they mean something very different and, in fact, incompatible in the programming realm. So if you want to help kids with math, or at least if you don't want to screw them up, it's probably a good idea to use a programming language where variables actually are variables and functions actually are functions. Or if you're going to use a different language, that's cool. Just don't call them functions and variables, because those words already have meaning. And math teachers, we had those words first. We had them about 3,000 years before everybody else, and we want them back. So that's one of the fundamental problems here, that if a kid doesn't understand what a variable is in their math class, and then they go and they learn how to program something like this, that's not going to help them. That's going to show them something that's completely wrong as far as math goes. So where we start with Bootstrap is, if we're going to build a video game, let's build it out of a programming language where variables really are variables, and where functions really are functions. So I just threw a ton of stuff at you about math and about programming and so on. And I just want to pause it. I don't know if anybody has any questions before I dive into what Bootstrap's all about and how we use it to build games.
The only question I've seen is, have you also looked at applying your product to the developmental ed programs that most colleges have?
I haven't. And not because I don't think it's a good idea. It's just we've been so focused on working with middle and high school math and computer science teachers, we haven't gotten around to that. But that's a really excellent idea, and I would be totally happy to talk about that if anybody wants to email me, and I'd love to have that dialogue and hear what you're thinking. Okay, so if anyone has any other questions, feel free to just throw them at me. The moderators will stop me and tell me that we've got a question. I'm going to dive in here and talk about how Bootstrap addresses this problem. So obviously I don't have time to give you the entire curriculum, so I'm just going to show you 2 techniques that we use in the curriculum to teach kids both to program and about math. So the first technique is called the circles of evaluation. So here's an arithmetic sentence down below, 6 minus 4 plus 5. And anyone who's taught math or who has kids who are going through math, you probably know that kids spend a ton of time trying to learn order of operations. And the whole reason that they spend all that time is because arithmetic, well, it turns out there's a literacy skill, right? These symbols, if I just jumble them up in a circle, these symbols by themselves don't tell us what order to evaluate things. There's actually a grammar that we as human beings invented. We call it, PEMDAS. We used to call it PEMDAS. So how do we get kids to understand this grammar? So what we do in Bootstrap is we show them basically sentence diagramming for arithmetic. So we show them a rule that says every circle can only have one function in it. So in this case, on the right-hand side, we've got 6 minus the sum of 4 plus 5. And you'll notice that instead of calling subtraction and addition operations, I'm really calling them functions, because that's what they are. And these functions can be composed with one another. So rather than dumping kids into algebraic syntax, right, f of x equals blah, 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 g of x equals blah, 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 and then asking them what is f of g of 5, instead of throwing them off the diving board, what we're doing is we're using the arithmetic notation that they're already used to. They know plus and minus. They've been doing it since they were kids. And we're giving them a visual spatial metaphor to think about order of operations that lends itself naturally to function composition. So if I just took my eraser and changed those symbols, so the circle on the right, instead of having minus and plus, had f and g, boom, that's function composition. That's all it is. So we're letting them reuse the notation they're familiar with, and we're giving them a way of assessing order of operations. And what's nice is that we can use those circles to translate computation, right? So here's the arithmetic expression 9 over 2 times 3, and you can draw the circle. And we can convert that circle into computer code. So we tell students, if you want to take that circle and compute it into code, we imagine a little ant crawling through the circle. And so when the ant is standing outside, he's trying to break into that circle. He has to cross over that curved boundary. And that looks a lot like an open parentheses. So we open our parentheses, the ant crawls inside, and the first place he goes is to the top of the circle, where he sees the division function. And then on the left-hand side, there's a 9. And on the right-hand side, well, look, there's a whole other circle. So we have to crawl inside that circle, too. So open parentheses, and we go to the can get back out. So we're just translating computation from one form into another using this visual spatial metaphor. And kids as young as 11 years old pick this up so fast you wouldn't even believe it. I actually visited a school down in Maryland that's using this with their 7th graders today, and they picked this stuff up in about 5 minutes flat. It was awesome. And once we have this metaphor, we can recycle it. So we can use the circles of evaluation to introduce Boolean logic, to introduce image manipulation, right? So we could scale or rotate images. It's a blast. And all the time, what we're doing is we're revisiting this algebraic concept applied to both numbers, but also to Booleans, strings, images, and animations. The other technique I just want to share with you is called the design recipe. And this is probably our most important technique. And it's about connecting these different representations of functions that I talked about. So here's a classic word problem. I'll give you a second just to check it out. So it's a word problem you'd see on a math test, or see it in a math book. And if you're a math teacher, especially if your state has embraced one of these Common Core type standards, a math teacher is going to ask students, well, how could you think about this function as a mapping between domain and range? How could you build a table of inputs and outputs? Right? So give examples after, what's the height after 1 second, after 2 seconds? Could you make a formula for it? Could you build a graph, right, to see what it looks like? So I'm going to show you how we actually do this in Bootstrap. And by the way, the software tool that we use in Bootstrap is called WeScheme. It's a browser-based software environment. So if any of you have web browsers on your computers, which I'm assuming you do, well, congratulations, you've already got the software. Just checking, guys. Can you see the web browser here?
Yes, we can see the web browser.
Great. Okay, so here's the word problem. I'll zoom in again a little further. Here's the word problem. And here's how we'd ask students to create a domain and range. We'd say the name of the function is height, and it maps from numbers to numbers. And if I'm a math teacher and I'm a stickler, I might say, actually it maps from real numbers to real numbers. That's okay too. I could look at it as a formula. So here's the syntax. We're defining a function height of d is just d times 1.5. And we tell students to show their work, right? We want them to give examples. So here's our table, right? Here's height after 1 meter. Well, that's 1 times 1.5. Height after 2 meters, that's 2 times 1.5. And if I click run, I can see the graph of that plane. All right, and that's kind of nice. That's handy, right? So we're no worse off than a graphing calculator. But a teacher could just as easily change things up and say, well, behind the scenes, I'm just going to swap this one line of code, and now we can view that's the flight of the plane on the background of a blue sky. Right? Real simple. And so we're using the technology just to make the process of solving this word problem come to life. Now, the other nice thing about this programming language is that it takes unit testing seriously. So let's say I'm a student and I've actually made a mistake. Right? So let's say I'm adding instead of multiplying. When I click run, right, so the plane takes off, and I can't quite tell if this worked or not. You know, it looks a little different, but maybe it's correct. But if I look in the editor, the compiler gives me feedback. It says, wait a second, you know, the actual value differed from what the expected value was. And I can click on a link, and it'll show me which of my examples didn't match my formula. And here with my example, I wrote, oh, it was multiply. That was the mistake. And over here, look, the second example, they're both breaking, and it looks like my mistake was that I used addition when my examples used multiplication. So I fix it, I go back, and there we go. No errors anymore. And so as a math teacher, we tell kids all the time how important it is to show their work. Well, now we actually have a good reason why. Because if a student shows their work, the computer literally checks their work for it. It'll make sure the formula matches the examples. So we're getting this really concrete connection between different representations. And of course, the end result is either a simple graph or a pretty picture, an animation of a plane taking off. So this three-step process is known as the design recipe. It's been developed at the university level for decades as part of the PLT community of research. And we use it in Bootstrap because it just so happens to be a phenomenal way of teaching students how to solve word problems. So what word problems do we do in Bootstrap? How does this build a video game? So here's the 10,000-foot overview. The very first lesson in Bootstrap, kids brainstorm a game of their own. And here are the rules. We say every game must have a background. So if it's a space game, maybe the background is the universe. If it's a sports game, maybe the background is a soccer field. If it's a forest game, maybe it's the forest. You get the idea. Second, every game must have a player. So maybe maybe a student says, my player is going to be a leprechaun, and he's traveling through space. Every game must also have a target, something the player wants. And every game must have a danger, something the player wants to run away from. So a student might say, all right, my space leprechaun is trying to capture gold, and he's trying to avoid, I don't know, broccoli, space broccoli. So at this point, all the students brainstorm their games, and for them it's really concrete, right? They're excited. They can see it in their minds. My leprechaun game is going to be awesome. I can see it now. And we channel that excitement, and we say, all right, now you're ready to program, and we introduce the circles of evaluation on day one. So again, that's that sentence diagramming for arithmetic, and you can see again how we connect the arithmetic directly to algebra. So students start typing in simple arithmetic expressions and getting them to evaluate. On day two, we extend the metaphor to other data types. So they're still reinforcing circles of evaluation, but now we're using other types, like images and string. And so kids are making shapes. And this is where we introduce domain and range, because these mathematical functions don't just work on integers and reals, they also work on strings, images, and so on. So at this point, what kids are doing is they're bringing in graphics to their game. So they find a leprechaun image, they find a space image, they find gold, they find broccoli. And they use these circles of evaluation to build an expression that will generate a screenshot, just a frozen image of what their game looks like. So kids are psyched. Right? They're like, all right, I can see my leprechaun game. It's not moving yet, but it's going to be amazing. Then we introduce defining functions, again using the design recipe. So we have students make a rocket blast off. And down below, I've got the three representations, right? The domain and range, the example table, and the formula. And when kids solve this word problem using the design recipe, they see a rocket blast off. And that's pretty cool. Kids are jazzed about the rocket. But you know that there's always that one kid sitting there going, but what about my game? Right? I didn't come here to make rockets blast off. I came here to make a game. And so for that student and for the rest of the students, we say, well, tell you what, this design recipe, this is no joke. If I give you a different word problem, you can use it to solve that word problem. And maybe the word problem is how to animate your player, how to animate your danger, your target. Kid says, really? We say, yeah, give it a try. So now students write code, same linear functions that they used to make the rocket blast off, but now their space broccoli flies across the screen. Their gold flies across the screen. And the kid says, this is awesome, it's moving. But then when the broccoli goes off the edge of the screen, it doesn't come back. Kid says, doesn't come back. This stinks. It should come back. We say, all right, well, when should it come back? And they say, well, when it's off the left edge of the screen. We say, well, when is that? Kid says, well, when his x-coordinate is less than 0. Ah, less than 0. So now we're talking about Booleans and inequalities in the plane. So we teach that math concept. So now they're writing functions that are actually inequalities in the plane. And they do a simple exercise to trap a butterfly. But it turns out that that exact same kind of math can be applied to word problems, that whenever the broccoli hits the edge of the screen, it now comes back on the other side. So for a second, kids are like, yeah, this is great. Broccoli's coming back on the other side. The gold is coming back on the other side. But wait a second. What about my leprechaun? I know how to make it go up. I know how to make it go down. But how do I make it do both? How can a function have two different behaviors? Well, that's where we introduce piecewise functions, right? Once again, here's the math to solve that thing that you care about. You want to build that part of the game? Here's the math for it. Some of you might remember what a piecewise function is back from your algebra days. So this is literally the piecewise function that will make the player move. And here's what it is in code. So if the key is up, we add 10 to the y-coordinate. If the key is down, we subtract 10. And this code looks a lot like the math because it is the math. And those of you who've programmed in other languages, this probably looks really different to you. And that's because, again, we're in a world where everything is pure math. And kids can extend this, right? They don't need to just deal with up and down. They can add all sorts of crazy cheat codes and different keys and all this stuff. So now kids are excited again. You've got the broccoli's moving and coming back. The gold's moving and coming back. The leprechaun can go up and down to chase the gold and avoid the broccoli. But what happens when the leprechaun hits the broccoli? Nothing. They just pass right through each other. Once again, the class goes, oh, this stinks. Something should happen. They should blow up or something. We say, great, okay. You care about that so much. Tell me when they should blow up. Class says, well, when they're touching, right? When they're close enough together that they're touching. And we say, aha. Well, how do you know how close together 2 points are in the Cartesian plane? Turns out that's just a Pythagorean theorem. And so instead of teaching the Pythagorean theorem and having kids measure like, ladders leaning against brick walls or rope on a flagpole or some nonsense, instead we're doing the same math and the same word problem, but instead of a flagpole, we're telling kids do this to make your leprechaun capture the gold or to make it blow up when it hits the broccoli. And so it's directly applying the math to something they care about in the service of building a game. And once that's done, once they've gone through the proof of the Pythagorean theorem, and by the way, when I say that this curriculum is made for kids, I mean sometimes we use manipulatives, right? We're not just writing code all day long. There's a lot of pencil and paper activities. There's a lot of this stuff. So these are actual Pythagorean triangles. We have kids prove the theorem, and then they type it in. And when they're done, there's a game release party. And I can guarantee you, those of you that are science teachers, oh man, your math teacher might not say it, but they are jealous of you. Because science teachers every year get to have a science fair where their kids show off what they've done. Math teachers, we don't get that. Parents come to a physics teacher's classroom and they say, oh, it's nice to meet you. My kid made a slingshot in your class. I know what you did. Kid comes to a math teacher, they say, I have no idea what my child does. That's why this video game release party is so fun. Because math teachers finally get to show a product. They get to say, look what your child built with algebra. They built a game. And these parties are a lot of fun. And we actually have kids not just show off their games, but actually present their code. In the industry, this is called a code review. And I think we all probably know at this point that just teaching kids to code is not enough to get a job. You want to work at Google? They don't care if you can code. They want to know if you can program. And part of a programming skill is being able to talk about your code to other people. So here we've got 6th and 7th graders from a middle school out in Redwood City, California, who are presenting their code at a demonstration, not just to adults and teachers and peers, but to engineers from Facebook who were kind enough to come and check it out. And they had to explain how they solved the word problem and why they made the design decisions they did to write this code. It was really cool. So the games. Here are 2 simple games superimposed over some of the code that it takes to write them. We've got a game called Shopping Sensation. This looks like this student has a shopper who's going through the mall trying to get money and avoid the plant from Little Shop of Horrors. Here's another game down below. It's called Death Valley. And it looks like that we've got a sweating banana who's trying to avoid the evil sun. And I'm not sure if you guys can see this out in Cyberland, but he's trying to capture a a suntan lotion tree that's floating around in the Sahara, filled with suntan lotion. So the games, the games are pretty simple, but they're completely owned by the students. They made up every last component of the game, and they wrote the code for every last part of the game. And on top of that, they didn't just write the code. They can explain to you every step of their reasoning all the way back from the word problem. And so what we found is that, even though it doesn't look like PlayStation, kids are so engaged because they've mastered it. They can explain every last piece of it to you. So what does the curriculum actually look like? So as I said, the software is free in the cloud. Nothing to download, nothing to install. If you've got a browser, you're done. The materials for teachers. So we've got incredibly detailed lesson plans. And if any of you are curious what those look like, I'm happy to share them with you. Feel free to ask me as a question when we're done here. All of our lesson plans, handouts, warm-up activities, exit slips, rubrics, assessments, workbooks. There's a detailed student workbook. All of this stuff is available for free on our website, and it's aligned to the Common Core and TEAC standards for mathematics. So if you're a math teacher and you're trying to figure out where do I fit this in my scope and sequence, all of that information is there for you. We offer professional development workshops, so we believe really firmly in the importance of giving teachers great PDs so that they feel confident about how they can go and bring this to their students. So we're partnered with districts, schools, and after-school programs across the U.S. So that's what we're all about. Students building something awesome using algebra. Video games are an incredible motivator. They're a great resource for teaching, not only because they're fun, but because every student has played them, right? Students have an intuitive understanding that broccoli should come back on the screen, that leprechaun should capture the gold or blow up when it hits the broccoli. So you can build on that and use that as a resource. Instead of saying, hey kids, you don't know anything about algebra, I'm here to teach it to you, we can say, look, you do know something about games. You know how it should work. And so you're going to ask me surprisingly expert questions about how to build your game, and because we've got the language right and the tooling right, those questions just happen to be in the form of basically word problems. And every word problem has an answer, and every answer is taken directly from an Algebra 1 concept. Our goal is that no student ever raises their hand and says, why do we have to know this? Because of course you got to know it. You want to make your game, right? So that's what we're all about. We believe that algebra is really important. It's the gateway to STEM. So if you care about STEM, you got to care about algebra. And we know from research that if you want to help students in algebra, you can't just shove a random program in their face. You got to do something that's going to actually address making functions concrete and connected. So how do we do that? Well, you got to start with an algebraic language, but you also got to aim for transfer. Right? You can't just say, all right, kids, solve a problem. You got to make sure that what they're learning, the skills they're learning, are directly transferable to a regular math test or to a regular math assignment. Otherwise, all they've done is made a game. And I got to say, learning how to code by itself is good, but I think we can do better. And so when I talk about transfer, we actually do evaluations, pre and post tests, where we give students straight up math tests to find out if they're able to apply what they've learned in Bootstrap on a regular pencil and paper math test. And we found statistically significant improvement from students around the country on this sort of thing. So we're really excited to have that data. And it all comes down to learning. Right? We didn't start saying, this thing is awesome, what can we teach with it? We started with, kids need help with algebra. What are our learning outcomes? And we built backwards from there. So that's what we're all about. My email address is down below. You guys have been awesome. We got plenty of time for Q&A. So thank you so much for your time. And I guess let's open it up.
All right, we have some questions here. So one question is someone from YouTube saying, did he say free?
Yes, indeed. I did say free. So I'll just show you real quick what that looks like. Let me turn screen sharing back on. Let's see. Hopefully you guys can see a web browser now. So here's our website, bootstrapworld.org. Can you guys confirm that you can see the website?
Yes, we can see the website. Yep.
Great. So if you go to this website right now and click on materials, you'll see that we've got two different courses, Bootstrap 1 and 2. I'm just going to click on Bootstrap 1. We've got a list of all the math concepts this covers, so Bootstrap 1. So here's every single lesson plan. Here's what it looks like. Here's Unit 1. Every lesson plan includes an agenda. It includes the Common Core math standards that are addressed in that lesson plan. It's got a vocabulary list, a list of materials. And the lesson plans are incredibly detailed. So it's written almost like a textbook, but don't worry, every good book has teacher notes. So here are notes for teachers that goes further in depth for how to address students that are struggling or how to challenge students that are zooming ahead. We've got diagrams that recommend something you could draw on the board to drive home a concept. And don't worry, if we recommend that you use a picture of a dog, well, we're not going to leave you hanging to go find that because teachers are busy. We're going to give you a link to a picture of that specific dog in the lesson plan. So yeah, you can go and find your own, but if you're a busy teacher like I was when I was in the classroom, my goal was that every single thing you need is here. And of course, if you have any questions, there's a link to a discussion group. You can ask a question right as part of your lesson prep. So the lesson plans are all free. There's a student workbook that you can buy on Lulu for $8 a pop, but of course we also provide a free PDF of the same book. So if you have access to a printer and it's cheaper than $8 a pop, here's a student workbook. It's about 50 pages long. There's tons of stuff in here. And these are all pencil and paper activities you can give to students to supplement what they're doing, to have them show their work, to bring home for homework. And we've got standards alignment to Common Core, TEKS, CSTA standards, anything you can imagine. All of this is free and online right now.
All right, another question is, what is the youngest age that students have used this at?
That's a great question. So the sweet spot for us has always been sort of 8th and 9th grade, but the real test is when are students ready to learn algebra? So you may know students who are ready to learn it in 5th grade. You may know students who are not ready until 10th grade. So there's a school district in Maryland named Anne Arundel County Public Schools, and there are some teachers there that have been using this with their gifted and talented 5th and even 4th graders. So I think, to my knowledge, that's the youngest it's ever been used with.
Thank you. And it looks like there's some questions here. Is there a difference in the interest between girls and boys?
You know, we actually haven't found that. And I think one of the reasons for this is that while there's some evidence and research that looks at the different kinds of games that girls and boys are interested in playing, we're not playing any games. Girls and boys are equally interested in building games. I don't know if some of you are familiar with NC-WIT. NC-WIT is basically where to go to find out how to engage girls and young women in computer science. And they've actually published a list of best practices, and a lot of those are integrated into the curriculum. One of them is, girls are often most intrigued by a project that they see as being valuable or helpful to others. So we always recommend to teachers, and we cover this in our workshops, that don't just tell kids, hey, you're going to build a game. Give them examples. And for girls in particular, it's important to give examples that deal with things like, what if you're going to build a game to teach your younger brother or sister about healthy eating? How could you build a game about staying fit? Maybe to teach your grandmother or grandfather or aunt or uncle how important exercise is. Give concrete examples for games how that can really be helpful. And we find girls are really excited by this sort of thing.
Okay, and another question is, someone is asking, it's a two-part question. I'm curious how this is being used in after-school programs, and they're also interested in what kind of professional development and support is offered.
Yeah, so I think it depends a lot on the kind of after-school program. So after-school often has this reputation of being like a drop-in program, like you just sort of show up whenever you want. Other after-school programs are a little more rigorous, and there's an expectation that students are going to be there every day, and that what they're doing is actual, it's not just blowing off steam, but it's academic. So for academically focused after-school programs, Bootstrap has worked great. I'll give you two examples. There's two after-school networks. One is called Citizen Schools. One is called Higher Achievement. And I think Bootstrap definitely falls on the most rigorous end of what those two networks offer. But Bootstrap has been used successfully in dozens of classes in after-school programs like that around the country. Just in terms of dosage, we recommend blocking off at least, at a minimum, 2 hours of contact time per week for students. Anything less than that, and basically you're winding up spending more of your time reviewing than you are teaching. So different after-school programs will offer that somewhat. And as far as PD offerings, so we offer a 3-day workshop for teachers, and this workshop is awesome. It's soup to nuts. We go over some other research on algebra education and programming education, but 90% of the entire workshop is hands-on PD. So we put teachers in the roles of students, and we actually walk through the entire curriculum, start to finish. Any activity that we're asking you to do with your students, we're going to model for you and have you do it yourselves, so that you're going to run into the same questions, the same problems, same challenges, same ideas that your students will have. And then we stop after each activity to debrief. So we say, how is this going to be differentiated for learners who are struggling, learners who are advanced? And so by the end of the 3-day period, not only have teachers seen the entire curriculum modeled, but they've had the opportunity to reflect, to ask questions, to build their own video game, and to go home with a solution set, right? They've got the workbook that they've completed that's all of the answers already in it. So that's what our PD looks like. On our website, again, we have a list of workshops on the workshops page. Keep an eye on that. We're always adding new ones. Teachers can come and attend. We've got a great one scheduled next week in Massachusetts, and another one the week after in New York City. And as far as support, every single teacher in the world has access to our free online support community. So you can post questions, and not only is the Bootstrap staff on there answering questions, but there's hundreds of teachers from around the world who are there answering questions as well. We do also work with individual districts. So for example, DC Public Schools, Fort Lauderdale, Florida, through code.org. We work with New York City Public Schools, work with some other districts also as part of code.org. Districts, we have special contracts, so we provide higher level support. So not only do you have the online discussion group, but we'll do Google Hangouts. We'll get on a plane and come to a district for a week and actually spend time visiting your classrooms and giving you feedback, answering questions, talking about ideas. There's a lot of support for teachers who need it.
I have a funny question about your games. Can you add sound?
Yes. It's not part of the core Bootstrap 1 curriculum, but I'll just leave it at it is doable.
Okay. I mean, when that broccoli hits the gnome, it has to make a noise.
You're absolutely right. You're completely right. Well, and that's what's so cool, right? That everyone who's played games, they know clear as a bell. Well, this has to work this way, right? It just should work this way. And so by drawing on that knowledge, all of a sudden, as a math teacher, I have the ability to say, you know what? You already know what you're trying to do. All you need is a little math to get you there. And so suddenly, math becomes an answer to a question that students have asked that they care about. So I love that you just knew this thing has got to have sound.
I have just a personal question. Do you play games, Emmanuel? Video games? Or do you have time?
Not only do I not have time, I actually never really played many video games, which is kind of weird and ironic, right?
Yes, it is.
I don't know.
Oh, we have one more other question regarding grade level again. They just want confirmation. What was the ideal level again?
So the vague but most accurate answer is the grade at which students in your school or your district take Algebra 1 is the sweet spot. The short answer is, for most states, that's about 8th or 9th grade. But again, your mileage may vary. So wherever you think Algebraic is appropriate to introduce, that's where Bootstrap is appropriate.
Thank you. I'm going to go ahead and refresh, see if I can see if we have any other questions. Someone is asking, I think they attended us a little bit later in the presentation. They're asking you, what language, again, did you use?
So the language we use is called Racket. It's a derivative of, it's very similar to Scheme or Lisp, if you're familiar with those.
And as you said before, you do have the web-based compiler that they'd be able to use with their browser.
That's right. If you have a web browser, you're in. That's everything you need. And I should add, it's not just like a random compiler. If you've ever taught kids programming and you've dealt with compiler error messages, you know how painful they are. We've built an environment where the error messages are unbelievably helpful. They're phrased in plain English, and they're even color-coded. So if you have students who don't like to read the error messages, the messages at least have colored segments that they can click on, which cause the relevant portions of their source code to blink. So it's really thoughtfully designed to be appropriate for an educational setting and for children.
All right, I think we are approaching the end of our hour here, and looks like the YouTube channel is quieted down now. So, well, thank you very much. It was very informative. It is something that's I think interesting to a lot of us, especially. It's not in my area, but my fellow associate dean does a lot of that dev ed piece with the math, and I know that this is a very important conversation we're having at the college level. Is how are we helping out our students who are coming in, and it's not just just traditional students coming in, but we're also looking at how can we find innovative ways to go ahead and look at how do you help returning adults who may have not been in a math class for quite some time. So
Absolutely.
It's always looking for new tools there.
Absolutely. Cool. Well, hey guys, thank you so much for your time and for inviting me to do this. This is really really fun.
Thanks, Emmanuel. We'll make sure and well, you have the link to where this is going to be, the GamesMOOC channel.
Mm-hmm.
Okay.
All right, everyone. Thanks for watching, everyone. We'll see you guys later online. Goodbye.
Bye.